Let's talk about the derivatives and integrals of power series. One of the whole reasons we got into Taylor polynomials and sums, infinite sums and such, was that we thought, hey, well, it's easy to take the derivative of polynomials, it's easy to take the integral of polynomials, so let's actually practice that now. We're going to start it on problems where we know what the answer is, and then in the next video, we'll take a look at problems where we actually don't know what the integral is and find out something about the integral. Let's do the integral of cosine x dx. So we'll write cosine as a Maclaurin series. So remember how that goes. It's 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus dot dot dot. Then what's the integral of that? Well, what's the integral of 1? We're just going to do this term by term. The integral of 1 is x. The integral of x squared is 1/3 x cubed, and we have a 1 over 2 factorial. The integral of x to the fourth is 1/5 x to the 5, and we have a 1 over 4 factorial as a constant multiplier. Integral of x to the sixth is x to the seventh, 1/7 of that, times 1 over 6 factorial, etc. And then let's simplify. X is just x. X to the third is fairly straightforward, but what about this 1 over 3 times 1 over 2 factorial? Well, 2 factorial is 2 times 1, and we're basically multiplying these. We are. So this is 3 times 2 times 1, which is 3 factorial. So we get 1 over 3 factorial. This is 5 times 4 times 3 times 2 times 1. So that's 5 factorial in the bottom. And then this is 7 times 6 times 5 times 4 times 2 times 2 times 1. So that's 1 over 7 factorial x to the seventh plus dot dot dot. And we recognize that as the start of the Taylor polynomial, a Taylor series, or a Taylor polynomial to 7th order of sine x. We're seeing that sine x pattern with the alternating pluses and minuses and only the odd powers and the factorials. So in some sense, we just proved that the integral of cosine x is sine x. Maybe not a surprise, but it'll be useful later when we're going to tackle integrals where we actually can't take the antiderivative of the original integrand function. That we just did some practice with integrals. Let's do a practice with derivatives. Let's think about 1 over 1 minus x. I know that's not a function we use all that often, but we're going to use it here because it has a very nice Maclaurin polynomial. If we thought of this as 1 over 1 minus r, we'd say, hey, that's a geometric final sum formula, and that would be r to the 0 plus r to the 1 plus r squared plus r cubed. And so now I just do all that, but with x. X to the 0, I could write that as 1. X to the 1, I could write that as x squared plus dot dot. Let's do x to the fourth plus dot dot dot. Then let's take the derivative. What's the derivative of 1? It's 0. What's the derivative of x? It's 1. What's the derivative of x squared? 2x. Derivative of x cubed? 3x squared. Derivative of x to the fourth, 4x cubed plus dot dot dot. Let's try writing that as a general term. So let's say, what's a sub n here? Remember, that's the coefficient on x to the n. So what's the coefficient on x to the 2 is 3. Coefficient on x to the 3 is 4. So it seems like we're saying the coefficient on x to the n is n plus 1. It's kind of tricky here. Up here, this was my n equals 0 term, this was n equals 1, this is n equals 2. So let's write that here, n equals 0, n equals 1, n equals 2, etc. But in this function down here, n is whatever the power on x is, so this is my n equals 1 term, this is my n equals 2 term, this is my n equals 0 term, and my n equals -1 term is apparently 0, so I can just ignore it. Pretty happy about that. Does this still work at n equals 0? Let's think about that. So this would say a sub 0 equals 0 plus 1. And is that the coefficient on x to the 0? Yes, it is. Coefficient on x to the 0 is 1, so that works. So that was good for us to check. So we got a derivative here of a function we could have taken the derivative of anyway. What is 1 over 1 minus x prime? Well, we could write that as 1 minus x to the -1 prime. So we'd get -1, 1 minus x to the -2 times 1 minus x prime for the chain rule. So that'd be -1, 1 minus x to the -2 times -1, or altogether negatives cancel, so we get 1 minus x to the -2. So what we got is this power series is the Maclaurin series for that, because here we took derivatives term by term, here we took derivatives of the formula the usual way, so we got the Maclaurin series for that function. So that's a way to get a Maclaurin series without having to take each individual derivative using chain rule and power rule and all that stuff. So next we'll go tackle some integrals that we can't take the antiderivative of the usual way.